Thank you.
For action.
Thank you, Chris, for agreeing to prepare this. Welcome.
Perfect. Well, let me first return the thanks to you for bringing us all here. I'm actually really excited to meet so many faces to put together with the names I've been reading at the top of papers for the last few years. This is fantastic. Thanks for making it happen. I wrote the title here so that you can orient yourself and you know you're in the right place, and then I'll erase it to leave me more room. I noticed on the program that there's a hyphenated title with a right side. I'm going to punt on almost everything that's to the right side of it because it's incredibly ambitious. But along the way, I'll try to say a few words to support it, at least to go in the direction that it was trying to lead me.
Yeah, sorry, I tagged that on there in an early draft version and never erased it because you never complained.
So the thing I want to talk about today is very much in the same vein as Vilke introduced us to in the previous talk. This is the idea of trying to learn something about strongly coupled field theories, which we care about from physics at RIC or at the LHC, and using holography as a tool to do that. Unlike Vilke, I'm never going to try to show you a plot that makes a direct connection to something that came out of the LHC. Instead, what I'm really interested in is taking the broad stroke features of this goo, this quark gluon plasma that's produced in RIC, and trying to incorporate those features into my holographic model, and trying to understand if I take just the most important ingredients, or what I deem to be the most important ingredients, how much the sort of holographic predictions change. And I'll explain all of this in the coming whiteboards. Also, I want to give a quick advertisement. I want to say that both Vilke and Paul Chesler really motivated my own interest in this sort of thing. I mean, there was sort of a really action-packed numerical year where Paul and Larry Yaffe released this huge tome that sort of spelled out all their tips and tricks. And I'll give you the archive number shortly, but I'd encourage anybody that really wants to know this stuff to look both there and in Vilke's thesis, where I learned a lot of this stuff. And also, let me say that almost everything I talk about today comes from discussions and collaboration with Taka, who's sitting right there, and Ilias Kiritsis, who sort of was our supreme overlord in Crete for many years. Okay, so my idea for this talk was to explain all of the words in the title one by one, and then assemble them again at the end. So I've already erased it because I was a little over-eager, but the first one was thermalization. So let me just write here. Thermalization. So that you remember where we are. And you should tell me if you can't read what I've written, or if I'm standing in front of it. So what do I mean by thermalization? This is the process that I really want to understand. And I want to understand it for reasons that Vilke already introduced before. I want to understand how a strongly coupled field theory that's initially perturbed away from equilibrium re-achieves some sort of equilibrium. So to put that pictorially, let me take my field theory, which lives here, and I want to do some sort of perturbation to it. That's my perturbed field theory. How might you do this thing? So operationally, what I'm really trying to tell you is that if my field theory is described by some effective field theory, if my system is described by some effective field theory, there's some Lagrangian I can write down, what I want to do is turn on some source, which I'll call F naught, that varies in time and couples to some operator that I want to perturb my system with. This is sort of the calculation that I want to do. Of course, in general, this is difficult. And this is where holography is really going to attempt to save the day. So the question is, once I do this, I prepare this out of equilibrium state, and I run the clock forward, where do I end up? So this arrow means wait some time. And after a while, my field theory will be in a new, or my system will achieve a new state. And I want to understand several things. One, I want to understand how I got here. So this arrow hides all the details of how my system equilibrated. I want to understand how that happened, and I want to understand, so let me write that. How? And I want to understand where I am. So what is this state? And these are questions that in principle depend on the parameters of the perturbation that I do to the field theory, that I've done to the initial state. And so both of these things are the sorts of data that I'm after, that I want to know. That data Go ahead.
When you prepare the perturbation, do you care if, like, what kind of a state it is? Is it a pure state, or is it a, I mean, do you care about?
So in principle, I very much care.
Yeah.
In all the examples that I'll talk about today, like in Vilke's case, I'll mostly be interested in a thermal state.
But you don't prepare the thermal state.
So what I'll actually be doing, as you'll see, is, okay, let me tell you what I want to do, and I'll tell you what I actually do, and I'll tell you why. What I'd like to do is start off in the vacuum and perturb it in some way and see what happens. What I will really end up doing is starting in a thermal state with a very small temperature, and I'll tell you why, and then I'll perturb that. So the answer to your question is a little bit complicated, but I'll motivate exactly why I answer it this way. Okay, so the point is, I want to know how I got here and where I am. And this answer, you can encode in many different sort of field theory observables. Maybe the most straightforward is in the various one-point functions of the gauge invariant operators in your theory. So if I'm talking about a large N field theory, which I will, maybe the single trace operators, things like the stress energy tensor, so these one-point functions, or in my case, I'm going to end up perturbing this state with a scalar operator, and so I can measure the time dependence of what's going on in my field theory by measuring these response functions. This is what I'll do. So let me just emphasize that I'd like to compute these things as functions of time. This will tell me both where I'm going and how I get there. It's not the only things you can measure. And in some sense, when you're asking questions about how a system thermalizes, the answers that you get back will depend on the sorts of probes that you use to answer those questions. So I'll say briefly at the very end, maybe if I have some time, I'll give you some examples of other types of probes that you can use and say why they're different from these and what you can learn from them. All these things are interesting questions. Right, so I'm going to perturb the field theory, I'm going to measure the response here, and I want to know where I end up. So it might be that at late times, these one-point functions, so let me just focus on this guy. Actually, it doesn't matter. I just don't want to write it twice. So it might happen that at late times, my system equilibrates, which means these one-point functions are no longer time-dependent. And it may be, it might be true, that this one-point function can be written, as a trace over some thermal distribution. So I take the average with respect to some thermal partition function that's relevant to whatever ensemble I care about. It's not important. If this happens, I'm going to say that the system's thermalized. So all of that is to tell you what I mean by thermalization. If it happens that my perturbation results in an equilibrium state where the one-point functions are independent of time, and they can be written in this way, I'll say that the system is thermalized and thermalization has taken place. That's what I mean by thermalization. Okay. So again, I want to know, I should just use the other board. I'm not being very efficient here. I'll warm up to it. I want to know how strongly coupled matter thermalizes. That's my aim. Okay, what do I mean by holographic? Of course, for those of you that are sitting here, you already know exactly what I mean by holographic, but let me tell you why it's relevant to this problem. The point is, I want to use my intuitions from gravity to understand this process. And so what this means is, I know via holography and the ADS-CFT correspondence that a thermalization procedure, a perturbation to a field theory, should have a dual geometric description. So if I draw again the same pictures, in terms of geometric variables, so these ones that you've been learning about the last days from all these guys here, I should have some space-time that's maybe time-dependent. That's my picture of time-dependent space-time. So my initial state should be, I'm going to perturb some geometry, maybe some black hole. I'm going to perturb some geometric solution. I'm going to wait some time, just like in the field theory picture. And in the end, it may happen that this solution, when I run the clocks forward via the Einstein equations, it may happen that this turns into a black brain or a black hole, and it's a static solution. And if this is true, I'll say that this is the holographic description of a thermalization procedure. One point I wanted to make that I didn't on the previous step is that the dynamics here is very obviously controlled by the Einstein equations, which you can write down and you can solve in the ways like Vilke was telling you before, or like you'll learn more about in the coming days. And of course, encoded in those equations have to be all the relevant equations that tell you how the field theory evolves. And one that I'm going to focus on a lot in this talk are the various ward identities that govern that time of dependence. For example, the fact that the energy density of your system is conserved up to, let's see, maybe you could say the work that you're doing on it by inserting the scalar. So the picture I want you to have in your mind is that I'm going to take my field theory and perturb it by pumping in some energy with a scalar operator. In the holographic side, what that's going to mean is that there will be some scalar field in my bulk system whose boundary conditions I'll end up changing, and I'll make all this much more precise soon. I'm going to evolve that system, that geometric system, by solving the Einstein's equations numerically. And at the end of the day, I'm going to use, again, the ADS-CFT dictionary to read off my one-point functions in the field theory. So this is the sort of philosophy for what I want to do. And of course, the great advantage that I've bought is that I can use all these tips and tricks that Vilke started to tell you about, that you'll learn more about, to solve the Einstein's equations, which is at least gets me in the game. It's a well-defined procedure, at least in principle, whereas in a strongly coupled field theory, I might not even know how to get started. So you see, I've actually accomplished quite a bit by mapping that problem onto a geometric one. Great. So the other advantage that I have is I can use everything I've learned about solving the Einstein's equations, about general relativity, to inform my sort of expectations for what I think should happen. And let me give you an example of why this is particularly powerful. So I'm going to plot on this side the expectation value for one of my operators. It doesn't matter which, you can put stress energy there if you want. Here's time. And let me think about what I would expect the geometry to do after I perturb it with this scalar. So I have some static solution initially. There's let's say a black hole with some scalar hair somehow, and I wiggle this scalar. I know right off the bat that there should be some regime that's governed exclusively by the time scale of my perturbation. So what I mean by this is, let's say this source that I'm turning on is a Gaussian with a width tau. Then I know that my response, generically, will have some regime that roughly matches this time scale. After that, I can't say much. Right away, all I know is that the Einstein's equations in general are nonlinear, they're complicated, and maybe the response has some other weird regime that's like a mystery regime that I'll call T nonlinear. So here's another time scale in my problem. What I want to do here, my reason for drawing this plot, is to introduce the idea of associating time scales to the evolution. And I want to understand how these time scales are important and what I can change in my theory to give more time scales, let's say. Okay. And I also know, as anybody that studied black holes in some detail, or maybe you learned about the last days, I don't exactly know, but I know certainly you will learn from Stefan, is that black holes respond to small perturbations by ringing down. So this is the sort of quasi-normal mode statement. Let me draw it first and then I'll talk about it. This is the idea that you should have in your brain, that a black hole's horizon acts in many ways like a damped harmonic oscillator. So this is my picture of a damped harmonic oscillator. And this horizon responds to the linear perturbations in a way that can be decomposed in terms of the quasi-normal mode spectrum of some system of springs and damping terms. And so if you don't know this already, I think you'll learn it. And if you do, then you know exactly what I'm talking about. The important point is that I generically expect that at late times, as my system thermalizes and the perturbation is sort of dissipating and I'm approaching my final state, that the way it will do so generically will be via the quasi-normal mode spectrum. Specifically at late times, the most real quasi-normal mode will play the largest role. It's the one that dies off last. And these perturbations will sort of bring me in to the final state. Now, the reason that I'm making this point and sort of harping on it is because in the vast majority of holographic thermalization calculations that have been done in the Poincare patch, as soon as you perform this perturbation, you almost immediately transition to this ring down regime. So let me write this, T ring down. This just means the sort of linearized regime. So in basically no example that I can think of, in asymptotically in the Poincare patch, in holographic thermalization, do you have some really interesting nonlinear regime here. You sort of do this perturbation, you pump in some energy, and you form a black hole almost immediately. And in fact, there's a large history of analytic results that show that you can think of it exactly in this way. Of course, the thing I'm interested in most is what I can do to my bulk theory to get at some interesting regime here in the middle. Is it always true, necessarily, that I'll end up, once I go, is it always true that I'll go immediately to this ring down regime, or can I somehow build in some interesting nonlinear behavior?
I guess perhaps, at least the way, where if you have non-trivial dynamics in some directions instead of only homogeneity, then I think you cannot at least neatly interpret it as being ring down. Like,
if there's a momentum dependence, for example, there might be a hydrodynamic regime as well.
Yeah,
right?
but at least nobody did it in that way, so I think there...
Right. I'm going to talk about homogeneous perturbations.
Then I think you're right.
And in that case, this is true. Right.
So, sorry, what was the difference? What is the perturbation way?
Well, at least, like, for instance, shock waves, I wouldn't know how to see this as a real ring down. I mean, there must be some hydrodynamics which does ring down, but the original shocks, they keep on going, and it's not obvious how to...
But
there
very late
might be one
time.
example of nonlinear...
Sorry, I mean, isn't the energy finally going to be dissipated across the system at very late times? I mean, it has to get there somehow, right?
Right, but
Even
there's a rather long time between...
And the reason here, I'm almost sure, is because you have a momentum dependence. Let's say you have some hydrodynamic regime as well. Because, there's a spatial dependence.
Right.
Which I don't have here. I'm not going to talk about that. Great. So, also from this picture, what I want to do is define a thermalization time as the sum of all these interesting time scales. So all the TNLs that you have, maybe there's many, and the ring down regime. But I don't want to focus on this part, on tau. I won't include this in my definition of a thermalization time, because this is a me-defined time scale. This is how long it takes me to drive the system from equilibrium. So I'm not interested in that. But it's there, surely. Also, I want to say one way you can sort of heuristically understand the fact that all these holographic examples immediately sort of dump into this ring down regime is because in the dual conformal theory, which is conformally invariant, the only scale that you've introduced is the temperature of your horizon. And so this time scale should also be somehow exactly correlated to that temperature. And indeed, the quasi-normal mode spectrum, as many of you know, it goes linearly like temperature, the frequencies of the ADS black hole horizon. And so it's no surprise in some sense that the only relevant time scale in those cases is set by the quasi-normal mode spectrum.
I would say it's a bit more surprising, right? Because there clearly is a non-linear regime, right? I mean, it could be there, and there are many scales in their initial state. When you do this sourcing there, you don't only have the temperature.
Right, but I don't care about this. I don't care about how I source. I don't care about those time scales.
But this
right? I mean, if you
kind of a linearized regime, right? So it's a ring that linearized around an equilibrium thing. So you would naively expect, if you push it very far from equilibrium, try to push it as hard as possible, that you're not in this linearized regime.
No. So I think we agree on this. I think it's surprising that you end up with this quick transition to the linear regime. This was one of the great early successes of this stuff from Paul and Larry. This is very cool.
But it doesn't follow from
I agree.
that there's only one scale.
Well, I mean, in a sense it has to, right? I mean, the location of the horizon, you can think about it this way also. If I'm just dumping energy in, and the only thing that matters is the location of the horizon, which is basically the inverse of the temperature, let's say, then the stuff's all just going to fall into the horizon. There's nothing to prevent it from doing this as quickly as it can.
I put scatter out. Well,
How? So I'm going to give an example. I'm going to give an idea for how I could build in some scattering. In fact, that's the point of my talk. Let me say also, to sort of follow this point, that everything I'm saying is specific to the case of the Poincare patch. In fact, you get much more interesting behavior in global ADS because there you have another scale. You have the radius, like Vilke explained very nicely on the board before. And so you can have scattering solutions, things that don't thermalize, all sorts of stuff. This is cool.
But even more perilous there, right? Because you can have initial configurations that settle into a black hole within an ADS radius worth of time, and then you have nearby initial conditions.
Except these islands of stability, as they call them. Things are very weird there. And but I sort of have the idea in my head, which I think is true, that answering whether or not these things can appear or whether you might expect them comes down to understanding how the different scales become relevant in different thermalization procedures. I mean, I think it sort of has to be this way.
Just a comment on the global ADS thing. That's even another reason for being cautious about that, and that's the paper by Steve Gupsa and friends, 2006 or so, where they basically looked only at coarse normal modes in global ADS. But if you look at it from a different angle, then basically it's it's dual to a actually time evolving plasma, right?
Yeah.
And so it's even just a static global ADS. You can, if you look at it in the right way, then it looks like a time evolving plasma to some extent. So maybe that's one more thing to disentangle.
Yeah, it's a good point.
I mean, you can look at fluid and flat.
You're saying that the coordinates were sort of boosted version of the static solution.
You can do many look at fluid in many different file frames from the fluid and on a sphere. That's the content of that, right?
But is there not more?
That's all. If you have a CFT has some is vial invariant, then I mean you could play the same game with the fluid in flat space.
Are you saying so? Are you saying if I did the same thing not in global ADS but in we could do that with any other?
Yeah. You always have. You could translate the fluid, the flat space fluid, to some other fluid, some other more non-trivial state in the curved space.
Right. I mean, but I thought in Steve's paper that the point was that you can perform some sort of symmetry transformation. Maybe
In some sense, what we're saying is it's just well known as a trivial transformation. So it's completely you can factor it out with the actual gravitational dynamics, and it's just it's not. But it's just interesting in the sense that when Steve did that paper, you could do just a very simple solution, a static solution, and still recover some sort of interesting phenomenological sort of model.
But I thought that's different from boosting a black brain, for example.
That's right. It's not a global symmetry
right.
of the theory on the sphere. I mean, you translate a fluid on the sphere to a fluid into Sitter space. And that's a translation that you can only do for an honest-to-God CFT. That's...
It's just a special conformal transformation, right?
I thought what he was doing, maybe I'm misremembering, that could well be, but I thought...
Sorry, we're taking you off. I take that on my... let's discuss it in the discussion session. But I think it's an important or interesting point to clarify.
Agreed. Okay, and let me just sort of bring it back by saying that this interplay between these different scales and the scales in your field theory, I think are in principle interesting, and I'd like to understand them better. And so everything I'm doing is going to be sort of geared towards unraveling how these things happen. Okay. All right, so there's one more important word in the title, which will also give you a good example of where I'm going with things. Confining. So what do I mean by this? So one way I can add a different scale into a field theory is by introducing the analog of lambda QCD, so a confinement scale. And in fact, this is what I'm going to do. What do I mean by confinement? Well, the normal diagnostic is the Wilson loop. I think throughout this talk I'm going to struggle to get the level right. And so I hope that if you don't understand what I'm saying, you'll stop me, because I really don't mind at all to explain it. And I'm not just looking at the students, for everybody. If you don't know, ask me. And if you do know and I'm going too slow, tell me that too. Okay, so confinement in a field theory can be diagnosed through this Wilson loop. You can think of it as taking two very heavy quarks and letting them propagate for a while, for time t. You can separate them by some distance. Okay. And you can compute this gauge invariant operator, the Wilson loop. And you know that roughly this thing should go like t times the quark anti-quark potential. So if you don't know this, you'll learn it in field theory class. Or you can ask me about it afterwards. Or if you do, then you're happy with this already. So if the field theory is confining, this tells you that this quark anti-quark potential should grow linearly. This is sort of intuitively what you would expect, because as you separate these quarks, the potential between them is growing, and it's more energetically favorable to pop quark anti-quark pairs out of the vacuum, and you get this sort of confinement. Basically, these quark anti-quark pairs arranged into mesonons, color singlets, and probably you know this story. But the important point is that a hallmark of confinement is this linear potential. Goes like d here. I'll just say f some constant. And when I put this in here, you get d times t, which is the area of this Wilson loop, and this is what people mean by this sort of area law. So often when you hear people talk about confinement, they'll use the phrase area law in the same sentence. That's what I mean by that. Okay, so the point is, any confining theory should obey this property. If I compute this Wilson loop in it, then I should get back an area law behavior. So what does this look like holographically? In fact, the sort of mapping of this Wilson loop calculation into the holographic variables, the geometric variables, is quite simple. If these are my boundary directions up here, you can think of this quark anti-quark pair as being connected by a string that dips down into the bulk. The action, the Navier-Goto action on the string, on the world sheet of the string, will minimize, the preferred configuration will minimize its surface area. So you can just compute this thing. And you can ask, given some geometry in the string frame, what are the conditions on the various functions that appear in this metric in order for this action to go like, what did I say, f b, f times b times t. What are the conditions on this metric that I end up with area law behavior for this world sheet? So I'm skipping the calculation here, I won't do it for you. But the point is, you compute this minimal surface, and you ask when, well, how does this metric have to look such that the Wilson loop, such that this minimal surface evaluates to this sort of area law behavior. And what you'll find out is that it's sufficient for the string frame metric, this warp factor A, which is a function of z. There should be some minimum at some finite z. So z is my holographic direction. And when I evaluate the warp factor there, it should be finite. The point is that this Wilson loop, computed holographically, will go like e to the minus t, a naught, a epsilon naught. Other stuff. exactly. Plus some other constant factors. This is the important part. Okay, so if I want to build in confinement into my dual holographic theory, what I need to do is make sure that my bulk metric, which is dual to confining state, has a warp factor with some minimum where the string can sort of just sit, and that the warp factor is finite there, so that I end up with a finite string tension. So that's basically the force between the quark anti-quark pair. There needs to be some finite constant. If I've done those things, then I'm guaranteed that my Wilson loop calculation will give me back an area law, and that the dual holographic state should exhibit exactly the notion of confinement that you would expect from a quantum field theory. And so I have sort of a slogan that you should keep in mind. These confining geometries, you need to sort of cap them off. So they need to have some end, some place where this warp factor achieves a minimum at some finite z. They need to have this cap in order for the string spectrum to be gapped. And so this is like a little mnemonic, so you can imagine what sort of geometries will be dual to confining states. Now, let me tell you which sorts of geometries those are. So the sort of prototypical example of a holographic confining gauge theory is what's called a hard wall. So this is sort of the 0th order thing that you might think. I told you that you need to cut the geometry off somewhere in order to end up with this gap in the spectrum. And in fact, the hard wall model just does that artificially. So you take your ADS space and you just artificially terminate it. So this is my wall at some z naught. Okay, as soon as I've done that, there's now another important scale in the theory, z naught, where this wall is. So now I can expect in my, when I do this string calculation, for example, as I separate the strings further and further, at some point this loop will just drop into the bulk and sit here on the hard wall, and it can't go any further down. So this satisfies sort of heuristically all of the requirements that a holographic confining theory should have. And if you go through this and you compute the mass spectrum of the glue balls, you'll indeed see that it's gapped with a gap that goes like 1 over z naught. The only relevant scale. Okay. So here's an example of a holographic confining gauge theory. And already at this level I can ask, what can I expect from doing a thermalization type calculation in this background? So this was something that we worked out with also the group in Brussels. And basically what happens is the simplest possible thing. So take this geometry and imagine throwing in a bunch of scalar stuff. So some homogeneous scalar, throw it in from the boundary, so now I'm pumping energy into the system. And what you can show, which should come as no surprise, is that if the energy density that you're pumping in is sufficient to create a black hole with horizon above the wall, you'll do so, and the state will thermalize. If not, then you'll have to worry about the boundary conditions on this hard wall, and you can end up with a scattering solution. So this is the solution that doesn't thermalize. And so this is a...
Is it really a fully consistent system?
No, very much not. I mean, it doesn't even solve the equations of motion. Okay?
Yeah.
my whole point is
how
just
do you
to...
set up the problem to make a black hole in this?
I mean, you can do it in the exact same way that you would do like a weak field perturbative calculation of throwing in scalars into just ADS, and apply ADS. What happens is... Exactly, that's exactly what I'm thinking. And so you can follow exactly the same thing. But look, nothing interesting has happened here. I mean, you could have guessed this already, right? If the perturbation doesn't even get to the wall before it forms the horizon, it doesn't even care that there's a wall there. If it does, then you need to worry about the boundary conditions, and do we have a way to know what the boundary conditions should be? No. The entire reason that this exercise is interesting is because it shows you that the existence of this other scale in the geometry, which plays an important role in the boundary field theory, can in fact have a measurable effect on whether or not a given perturbation thermalizes. It's very much an artificial, sort of over-the-top example, but it's also sort of in line with what you get in global ADS via the Shiraz and Hazara solutions. So this is sort of a warm-up For the
Say,
fall,
you know, the same physics that dominates what you just said will also appear, for instance, in Witten's black hole.
of course, very much. I mean, it's really just all governed by this confinement scale. It's the only thing
But
it can
like at a
defend on.
technical computational level, it also works out the same way.
In which way?
That in the using the weak field approximations, following Shalansky and Shiraz, that you throw in energy, that you'll get black hole formation multiple times.
Yeah, it's the same calculation. No, nothing's happened. Only the warm-up before you do the numerics. And in fact, those guys in Brussels continued and did the numerics in this to sort of match with the weak field results, and everything works the way you sort of know it has to do. They can follow these sort of scattering solutions for either Dirichlet or Neumann boundary conditions forever. I mean, they really just never collapse. Great. Okay.
These scattering solutions for the field theory, that would mean that you do not transfer momentum, you don't dissipate momentum.
Right. So this is a really weird thing that is not well understood. It's similar to the islands of stability we were talking about before in the theory on a sphere, where somehow you've pumped in some energy, but the system doesn't thermalize it. It's some equilibrium state, but it's not a thermal one.
Is it periodic in some sense?
Yeah, it's periodic.
In this case,
And it has
it's
beats
not a
and stuff.
fully self-consistent system of equations, though, because you have to neglect gravitational back reaction. So
Yeah, I mean, I've put a wall.
right, exactly. Yeah.
So I don't want you to learn. I don't want you to read too much into that. Only the point that I'm making, that following this sort of lead, that having a confinement scale can lead to interesting dynamics, might not be totally crazy. That's all. So now I'm going to follow that lead.
Sorry, one more question. Can
Yeah.
you interpret this as an extra conservation law? Probably not, right? Because you have
Which?
this phenomenon that if you have extra conservation laws, then, like for instance, in a 1D Hubbard model, you know that you cannot dissipate energy because the scattering.
You mean like related to integrability or something, where you have tons of conserved quantities?
Exactly, yeah, like
you
in
get
field
some-
theory, or but easier ones, you have this phenomenon. But
the point is, you shouldn't trust the scattering solutions.
Yeah.
yeah, that's what I'm trying to understand.
The point is the scattering solutions were almost built in to the way that the problem was set up by putting boundary conditions of a certain type at this wall.
Yeah.
And I mean, we're constraining exactly what the dynamics of the system are
So that is like a conservation law.
in a sense. I guess maybe.
Yeah, okay.
And maybe you can make it more precise, but I haven't really
Sorry,
tried
the
to do that.
system is ill-defined.
Is it
Like the system, you're not consistently solving all equations of motion.
Like,
when you
so
have
if you do this weak field perturbation, what he's saying is true. If you solve it numerically, in fact, the back reaction is taken into account. But at the same, so you might think maybe there's some growing instability from this scattering, but you're still just putting
But you're not
boundary
solving the
conditions.
ischial junction condition.
Exactly.
Yeah, so
I
the
agree.
system is ill-posed. Like,
Yeah.
I mean, you said it, I'm repeating what you already said.
Yeah, and I think it's worth emphasizing. His point is a good one. It's only to gain intuition. It's only as a
I guess you can imagine constructing a scalar potential, something like that, which mimics this kind of particle behavior, right?
oh, okay, you very much can. Let me tell you all about it.
Learns you a lot.
It's what I'm going to do right now.
Right.
As a matter of fact. Right. So as foreseen by Vilke, there's one way that you can sort of improve on this sort of holographic confining picture, and that's to build your hard wall out of something that the Einstein equations care about, something that your system really knows about and knows how to handle. And the way that we chose to do that was to add a scalar into the mix. So here's two pictures. This is a picture of the scalar potential as I move down the throat. And here's a snapshot of my geometry. So let me draw this in two different ways, and you pick the one that makes the most sense to you, because I haven't really figured out a good way to do it. The point is I want to build a wall out of this scalar stuff. So somehow I need the scalar to be really prohibitively large here and die off near the boundary. This is what my geometry is going to look like. I'm going to have a scalar that goes to 0 at the boundary, because I know I need to get back ADS. And as I go further down into the bulk, the scalar is going to grow. And what that means is that this potential will become very large, far in the IR. And I might hope that this potential is sufficient to scatter scalar perturbations, just like a quantum mechanics, 1D quantum mechanics problem, I might hope that this potential is wall-like enough to scatter these perturbations and give me some interesting dynamics. That depends on this confinement scale, which is built into this picture. So these sorts of models have enjoyed a lot of, I don't know if you could say success, but they've been very popular in the holography literature for a decade now. Maybe more, actually. My bulk action is going to be, let's see, how do I want to write this?
I mean, probably going, depending on how far one wants to go, I mean, if you relax the assumption of ADS asymptotics, then this black hole is exactly at this point once you reduce on the circle, right?
Yeah, so that's
the
also
work factor on the circle plays the role of your scale.
the confinement scale, exactly, yeah. Deflex squared plus B5, etc. So what I'm going to do, what I mean by introducing a scalar into the bulk, is I'm going to add to the gravitational action, the 5-dimensional action, some terms, a kinetic term and a potential for the scalar. I'm going to require that the potential for the scalar has this very property, that it blows up very large in the IR and makes this sort of wall. So, two important comments. The first is that unless I try really hard and I crank through some supergravity calculations in my favorite reduction, my favorite truncation, and work out exactly what this potential should be in a consistent supergravity theory, unless I want to do this work, it can be anything I want. So this is the difference between when people say something's a top-down model or a bottom-up model. So I don't want to try that hard. I want to make instead a bottom-up model. So I'm going to choose a V of phi that has this property. But it also has to satisfy a couple other properties, which are complicated enough that I'm going to copy them off here. The first is that just given a generic V of phi, for example, a mass term, I won't have this confining behavior for Wilson loops in the bulk. So the requirement that I want it to be a confining gauge theory already constrains what potentials I'm allowed to choose. So let me write this just as a point of note. That in the IR, I need my potential to go like this somewhat mysterious looking behavior. But this was worked out in detail years ago, and you can show that as long as your potential goes like this in the IR, you'll get back this area law behavior in your Wilson loop. This sort of makes sense that it should only be an IR property because it's what's happening at low energies. Confinement's a low energy phenomenon here. And so I want my potential to have this feature. And by tuning what happens in the UV, I can, of course, choose the dimension of my dual scalar operator. Squared plus dot dot dot. So now the game is this. If I tell you that I want to perturb my field theory by a dimension 3 operator, and I want that field theory to have confinement at low energies, I need to find the potential that goes like this in the IR and like this in the UV. Obviously, this still leaves a massive parameter space for various potentials. Sure. And there's some, you can compute an equation of state, a free energy from this. That's one type of solution that exists. Another type of solution that exists generically are black brain type solutions. So these take sort of the standard. Oops, that's not standard. Form here. Right. These have a horizon, these do not. These have the naked singularity, these ones don't. But these are the branches of solution that exist in this bulk theory. And so if you want to talk about the thermodynamics of the dual theory, the dual quantum field theory, you have to understand the phase diagram of this model, how these different solutions, what the interplay is between these different solutions when one is thermodynamically preferred and when the others are. So let me draw for you that map. Here's a thermometer. At low temperatures, there's only the thermal gas solution. So no matter how hard you try, for sufficiently low temperatures, the only solution that you'll be able to find is this, ones that look like this. As you raise the temperature slightly, eventually these branches of black brain solutions appear. We'll call it black brains. There's always the thermal gas solution. And for these sort of temperatures, what I'll call T naught, even though the black brains coexist with the thermal gas solution, thermodynamically, the free energy of the thermal gas is lower, and this is the preferred. This is the preferred state. For sufficiently high temperatures, above what I'll say called Tc, there's large black brains. And separating these two is an honest-to-goodness first-order phase transition. So if I plot the free energy, as a function of temperature, here I have thermal gas above Tc, so here's T naught, at which point there's a small black brain and a large one. So this branch appears. But not until the free energy goes negative in the small black brain branch is that the preferred solution. So here is Tc. Okay, so what I want you to take away from this plot is that even though these small black brains exist, they never dominate the thermodynamic ensemble. They're never the preferred solution. And they also, from this plot, you can see, have the interesting feature that their specific heat is negative. So, let's see, positive curvature, T squared, T squared. Right, so specific heat goes like the curvature of the free energy, and these guys have a negative specific heat. So, like Vilke told you before, these are locally thermodynamically unstable, these small black brains. So not only do they never dominate the thermodynamic ensemble, but they're also thermodynamically unstable. Nevertheless, they're going to play a large and prominent role in the problem as I've set it up. And so the question is why? Even though these small black brains are never the preferred state, they never are dual to the preferred state in the field theory, you don't end up there, they nevertheless have one redeeming feature, which is that a small black brain is in some sense a proxy for the vacuum, the singular vacuum solution, but with an IR regulator. So let me draw that so that it makes more sense. I said before that what I would really like to do is perform a thermalization calculation in the vacuum state. But this vacuum state is singular. The scalar blows up here. Does it make it singular? Yeah, does it make it singularity here? And as you could probably guess, that's extremely difficult to deal with numerically, computationally. No matter what you do, you're going to have to introduce some sort of IR regulator here. This is true in every kind of dynamical calculation. But it's especially dicey here because things are blowing up so quickly that you'll then have to study very carefully how the physics depends on where you've regulated your theory, where you've cut off the space. This could be very hard. How do you know when you've gone far enough? So that's the vacuum state. What do the small black brains look like? Well, they look basically the same, but they have a horizon far down in the throat. And this horizon gives you a sort of natural regulator in the sense that you know that the field should be well behaved there. It should be regular at this point. So this is the sort of under the table, slightly dicey magic that enables us to do our calculation. Yeah, go ahead.
Just maybe a stupid idea, but so these are both accessible states in principle to your system. It's accessible in the sense that, well, one is unstable and will decay into the other.
Sorry, so...
Yeah, no, you said that thermodynamically one is preferred over the other, right?
Right. The state exists.
And you could prepare the system in that state.
In principle, you can prepare this, and we will prepare it.
So
but it's thermodynamically unstable.
Okay.
And there's an old history about this, that there's a conjecture called the correlated stability conjecture that says that if you have a locally thermodynamically unstable solution, then this should be linked to a dynamical instability in the boundary theory. These are sort of like Gregory-Laflamme instabilities. These dynamic ones, but
not just in the boundary, right? Like the actual horizon is probably going to break up.
Exactly. This is that's what Gregory-Laflamme is. So there exists somehow some literature about the interplay between these sorts of black hole solutions and dynamical stabilities.
This is a conjecture rather than a theorem.
Very much so, and I think there's even counterexamples. I mean, this was I don't know, maybe.
I think part of the theorem is proven 4 years ago by Wolves and all that.
The theorem in the form that Chris was saying.
So originally,
Conjecture, yeah.
right. So there's this.
And there's some assumptions.
CSC, which was sort of an idea that, to the best of my knowledge, Guxer was the first one to elucidate. I mean, this is where the term CSC comes from, at least. Afterwards, I think like maybe it was Bushel dreamed up some counterexamples that didn't seem to go well, but I don't know the history very well, to be honest. But nevertheless, it's important to know that this sort of thing exists. There is one very important caveat, which is that because these are Gregory-Laflamme type instabilities, so these are instabilities, for those of you that don't know, to the horizon sort of clumping. So either clumps of charge or mass or energy density, and then sort of splitting like this. And as you might imagine, this is a spatially dependent process. And so if your perturbation is an S-wave perturbation, let's say rotationally invariant, you probably wouldn't see this even if your system had it. So we're actually going to use this knowledge to inform the types of perturbations.
I guess that's what I was aiming at. Like both of these states are accessible in a transient, at least in a transient regime.
Right.
Not at late time, but or in equilibrium state. But
I mean, they're honestly good solutions
okay.
from your theory. Okay. Now let me point out also. So everything I tell you is going to be performing thermalization in a state like this, a small black hole. Hopefully, because it retains enough features of the potential. So, you know, what I really want is a potential that looks like a wall. What I get is a potential that is almost a wall until I get to the horizon. And the question is, how small is small enough? So as I move this horizon and make the black hole smaller and smaller, I see more and more of this diverging potential. And so in this way, I sort of hope that I can regulate my system, my calculation, and get the important features of this confining geometry, which are the rapidly diverging potential. This is the philosophy. And I think in the remaining few minutes, I'll tell you whether or not that philosophy is a good one. Let me just also say that given this action, you can already go ahead and compute things like the speed of sound and see if your theory is QCD. Ours is not. I mean, it doesn't.